In this lesson, we're going to look at a system of two blocks, and it's the type of problem where one of the blocks is going to get pulled only, and we're going to look at the motion of the other block. So in this case, we're pulling on block 2, so we're not pulling on block 1 at all. There's a force acting on block 2, which we call F. So that could be a tension force. It could be, you can think of M2 might be a sled and M1 might be a child sitting on a sled. That would be a similar real-life example to what we're looking at. We're just pulling an object on top of another object, a cart, for example. So M2 is the cart and M1 is a box on the cart. So F is the force we're applying on M2, and there's friction between M1 and M2, both static and kinetic. So that's why I have that roughed up surface in here indicating that there's friction there. And what we want to analyze is how hard can we pull on mass 2 before we pull mass 2 out from under mass 1. So mass 1 relative to mass 2 would go off the back. Okay? So let me erase that because we're not going to talk about the relative motion of mass 1 and mass relative to mass 2 really any more than that. So in this problem, we're assuming that the system is already in motion to the right, and we're considering also we also have friction on the floor. So yeah, we're looking at the probably the more complicated of the cases where we also have friction between the floor and M2. All right, so where to begin? Well, we're always going to begin with force diagrams and try to identify all the forces in the problem properly. And I'm going to start from the top down. So I'm going to start with M1 and then go to M2. There's no reason you have to, but I think it's easier in terms of doing the analysis to start at the top and work your way to the bottom. All right, well, certainly gravity is in this problem. So we have mg, m1g pointing straight down here, and we have then, it's not, the block isn't sinking in to block 2, so there's a normal force on block 1 by block 2. And notice I have the frictional force drawn in to the right. Why is the frictional force drawn into the right? Well, anytime you want to understand what friction is doing, imagine the problem without friction in it at all. So if there's no friction between M1 and M2, when you pulled on M2, M1 would not move at all, right? So if there was no friction in here, M1 would not move. You would simply slide M2 out from underneath M1, and M1 would fall straight down to the ground below. Okay, now, as we said, in terms of the relative motion, as we slide M2 out from underneath M1 is going to want to slide backwards relative to M2, and if there's friction between M1 and M2, then friction is going to oppose that relative slipping, and friction is going to go forward. So that is why we have the frictional force forward on M1. It's because of the relative motion, and friction is going to oppose that relative motion and pull block 1 forward. So if block 1 doesn't slip, it moves along with block 2, and M1 and M2 move as if they're one object. So we have the frictional force on M1 going forward, and that is it. That is all the forces acting on M1. M2 is a little more complicated. So if we use our ons and bys a little bit, it certainly will help us out. So I'm going to erase some of this up here for the moment. Whoops. And now let's look at M2. Well, we definitely have gravity, M2g, pulling down on mass 2. And we also have the weight force of M1 pressing down on M2, but technically it's not the weight force, it's the normal force. It's the normal force on 2 by 1, which is the action-reaction pair. So these two, right, are an action-reaction pair. And if we look at what's going on in M1, that normal force here on 1 by 2 is going to equal M1G in terms of its value. So that's how the weight force from M1 is getting transferred to M2. It's getting transferred through this normal force. Then we also have a separate normal force on 2 by the ground, because 2 isn't sinking into the ground. We have our applied force, F, pulling up at this diagonal theta. And of course, friction we have between M1 and M2, and between M2 and the ground. And the frictional force on 1, right, dragging 1 forward, was the frictional force on 1 by 2. So that means we have an action-reaction pair here. There's a frictional force on 2 by 1, equal in magnitude, opposite in direction. And the opposite in direction should make sense. This is intuitive. If M2 is being pulled to the right, friction is not going to help it go to the right. So friction is going to be to the left. And then, of course, friction between the ground and M2 will also be to the left. So there certainly is a lot going on here with forces and action-reaction pairs, but hopefully we are getting to the point now where this language and the description of how the forces are acting is becoming more common to you and is more understandable. So let's clean these up again. So hopefully we understand these force diagrams. Now, when I go to write down Newton's second law to get the dynamics of what's going on, the equations that will tell me how the blocks are moving, I will always take the forces and use sines and cosines to get the force out of the quadrants and onto the axes in my problem. So I have an F cosine theta in the x direction and an F sine theta in the y direction, and I'll use those forces in my equations. Well, I'm going to do x and y directions for M1 and x and y directions for M2. And that is my equations 1, 2, 3, and 4 that I have highlighted in yellow here. So equation 1 is simply the sum of the forces in the x direction acting on mass 1. And there's only one force in the x direction, the frictional force forward, so it's positive, right, because it's forward, equals mass 1 times its acceleration. And I didn't put a subscript on the acceleration here because I'm letting them, for now, stay together. So I'm not letting them slip. So this acceleration would be the acceleration of M1 and M2 together up to the point where M2 could no longer be pulled any harder and accelerate any more, and then M1 would begin to slip off the back. So these equations with the A not having the subscript is for the system when they're moving as one. Now in the y direction, as I think we talked about earlier, the normal force just equals mg, and that's the normal force on m1 by m2. Now in the x and y direction for m2, I'm simply letting my force diagram guide me into my equations. I'm looking at the arrows that go forward and the arrows that go backwards for the x direction. Here I have a positive F cosine theta because it's in the forward direction. I have a negative mu static force normal 1, 2, so the frictional force, that action-reaction pair between 1 and 2. And notice here I do have kinetic friction for mass 2 in the ground because 2 is sliding against the ground, right? So we have static friction here and kinetic friction down here. And it is backwards. Both the static friction and kinetic friction are backwards, and then of course it's m2 times acceleration. And we said also that the ground, right, the force normal 2 on 2 by the ground has to be supporting both the weight of M1 and M2, and M1's weight is transferred to M2 through the normal force on 2 by 1, right, going down, that we've talked about as well. So those are the correct force diagrams, and those are the correct Newton's second law equations that describe what is going on in this problem. And those are the equations you are going to use to try to problem solve anything you were asked to solve for. Now, if we were asked to find the maximum acceleration, remember we said the equations above refer to when M1 and M2 stay together, and I can't pull any harder on M2 without having M1 slip off the back. Well, to find that maximum acceleration, and this you really want to put a star next to, because this is always a big trick in solving any of these problems. To find that maximum acceleration, you are only going to focus on block M1. So basically what we are going to do is pretend that M1 is all by itself on a surface that has a frictional force given by the frictional force in the problem, the static frictional force in the problem you're looking at. So let's say we know, and that's why I have the example over here, let's say we know the static frictional force is 10 newtons, because when I plug in mu static, let's say the problem gives us mu static and it gives us the force normal, I can calculate that maximum static frictional force. Well, that maximum static frictional force is what friction will actually supply up to. So in other words, if M1 is all by itself on the ground, then I could pull with 6 newtons instead of the 10 that I have shown here, and then the actual frictional force would be 6 newtons. 7 newtons, actual 7. If I get up to 10 point anything, 10 plus a smidge, right? The maximum static frictional force is 10 newtons, and at that point M1 breaks loose. So the way you get the maximum acceleration is you look at having a force of 10 pulling forward, right? And use the mass of M1 and calculate the acceleration just from F equals ma, right? So that would tell me the maximum acceleration is 5 meters per second. I think the best way to really understand this type of problem, in addition to you going back and rewatching this video, if you have to understand every single force that's in the force diagram for M1 and every single force that's in the force diagram for M2, and then to understand generating the Newton's second law equations, is to then look at a numerical example. And that's exactly what I have on the next page. So before going to the next, watching any more of this video, going to the next page on this video, what I would like you to do is stop the video right now, try the example on the next page, and then come back and unpause the video. So I'm going to ask you now to pause the video. And hopefully now you're back with me, and let's take a look at the solution that hopefully you were able to get. So what we have here is we have used equation 2 from the previous page. Now let's go back and remind ourselves what equation 2 was. Equation 2 was just to get the normal force and on 1 by 2, and we're going to use that normal force to calculate the maximum static frictional force. So that's what we do. This is the maximum static frictional force. We use that as our break loose force, divide it by the 10 kilograms. So this tells me then the maximum acceleration that both block 1 and 2 can have before 1 would break loose and slip off the back. Well, now if I want to know the maximum force, I'll simply use this acceleration in my equations 3 and 4. So for equation 4, that's our normal force again, because we're going to need that for the kinetic equation. So my normal force 2, remember, was m2g plus essentially the weight force from m1. And then I'm looking at the forces in the x direction on mass 2, and that's this equation here, where we get the F cosine theta forward, the static frictional force from mass 1, and now it's its maximum value, the 9.8 newtons. And here's where we needed the normal force between the ground and M2. We have the kinetic coefficient of friction, the normal force from 2 equals mass 2 times my maximum acceleration. So this is my maximum acceleration value gets plugged in here, and my only unknown is F, so I get the maximum force. I realized there was a lot going on in these last 2 pages, and these are problems that students need to take time to absorb and understand what's going on, and we have a couple of these types of problems in the homework packet as well. So hopefully this will be helpful to you, and again, we can, as always, talk about it more in class.